Now, in the characterization techniques, we have to study optical microscopy. Now, the principle of optical microscopy. An optical microscope creates a magnified image of an object with an objective lens and magnifies the large number of it magnifies the image to the further more and an eyepiece to allow the user to observe it by the naked eyes. Of the many techniques available for the analysis of solid materials, perhaps the simplest is the optical microscopy. Two modes of optical microscopy are typically employed based on the measurement of transmitted and reflected light from a transparent and opaque samples, respectively. Now, often a microscope is fitted with both modes, allowing one to analyze both type of samples. Most of the solid state materials discussed thus for are non-transparent in their analysis as grown as dissipate states. Further, it is usually difficult to prepare thin cross sections for transmission microscopy. Hence, materials scientists typically employ the reflection mode, also known as episcopic light differential interface contrast, that is DIC microscopy. This technique is useful for imaging a variety of reflective samples, including materials, metals, semiconductors, glasses, polymers, and composites. The semiconductor industry relies heavily on reflective DIC imaging for quality assessment of computer chips components. Surface artifacts such as depressions and particulates create optical path differences in the reflected beam. Formation of the final layer image is the result of interference between two distinct waves front that reach the image plane slightly out of the phase with each other. Unlikely the situation with the transmitted light and semi-transparent phase specimen, the image created in the reflected light DIC can often intercepted as a true three-dimensional representation of the surface geometry, provided as a clear distinction can be realized between raised and lowered regions in the specimen. Oftentimes, the reflected waves front imaging from the samples are separated by only refractions of a micrometer, hence, which is the much less than the resolution of the objective. Then there are some applications. The first one, the crystal morphology and symmetry. The crystal fragments, that is characteristic shapes, classify isotropic and anisotropic substances. Check possible symmetry, parallel extinction. Second application, face identification, purity and homogeneity. Standard optical data for comparison. It gives a reflective indices and optical axis. Phase analysis, that means the impurities with the separated crystalline amorphous phase. And next one is single versus the twinned crystals. You can make a very well difference between the single and twinned crystals. Now it identifies the crystal defects, grain boundaries and dislocations. Defects always present in even a single crystal. Chemical etching may be preferentially occur at a stress site. The fourth advantage of the application is refractive index determination. Now, there are some limitations. The resolution limit of optical microscope. When an optical microscope with a transmitted light is used at a very high modifications, the image of point objects may be destroyed. They may be seen as fuzzy disks and are surrounded by diffraction rings known as eye-ray disks. These diffraction rings limit the ability of the optical microscope to resolve fine details of the sample. The resolving power of an optical microscope is a measure of the ability of the microscope to distinguish between two adjacent structural details without the interface of array disks. The magnitude of differentiation and hence the resolving power of an optical microscope depends on the light wavelength and numerical aperture of the objective lens. As a result, there is a distinct limit of an optical microscope to view adjacent structural details clearly, which is known as diffraction limit of the microscope. Low magnification is one of the limitation again. The maximum magnification that can be achieved by an optical microscope typically ranges from 500x to 1500x. While this level of magnification has many purposes and can be useful for a number of practical applications, it is considerably lower than the magnification that can be achieved with electronic microscopy. Poor surface view, that is one more limitation. Similar to the magnification limitation of optical microscopy, the surface view of the sample with an optical microscope is sufficient for many purposes, but can be a limiting factor also. So these are some of the limitations. Now, the scanning electron microscope. The scanning electron microscope, SEM, is one of the most versatile instrument available for the examination and analysis of the microstructure, morphology, and chemical composition characterization. It is necessary to know the basic principles of light optics in order to understand the fundamentals of electron microscopy. The unleaded eye can dominate discriminate objects subtending about 1/60th of a degree visual angle corresponding to a resolution of approximately zero point 0.1 micrometer. Optical microscopy has the limit of resolution of approximately 200 angstroms by enlarging the visual angle through optical lens. Light microscopy has been and continues to be of great importance to scientific research since the discovery that electrons can be deflected by the magnetic fields in the numerous experiments in the 1890s. Electron microscopy has been developed by replacing the light source with a high energy electron beam in this section. So we will for a split second go over the theoretical basics of scanning electron microscopy, including resolution limitation and the applications. Now, the imaging modes. The secondary beam or secondary electrons, the most widely used to produce the interactions of the primary electron beam with the specimen in the secondary electron emission signal. When the primary beam strikes the sample, causing the surface isolations of the specimen atoms. The ionization of the specimen atoms strikes the samples of the surface. Loosely bonded electrons may be emitted, and these are referred to as secondary electrons. As they have the low energy and typically the average of around 3 to 5 electron volt, they can only escape from a region within nanometers of the material surface. So secondary electrons accurately mark the position of the beam and give topographic information with a good resolution. Because of their low energy, secondary electrons are readily attracted to a detector carrying some applied basis bias. The secondary electrons are used principally for topographic contrast in SCM, that is scanning electron microscopy. For visualization of surface texture and roughness, the topological image is dependent on how many of the secondary electrons actually reach the detector. A secondary electron signals can resolve surface structures down to the order of 10 nanometer or better. Now, some of the applications of scanning electron microscope. These are materials used since for research, the quality control and failure analysis. The SCMs are very much useful in the research work, quality control and failure analysis. In modern material science, investigations into nanotubes and nanofibers, high temperatures, superconductors, mesoporous architectures and alloy strength are rely heavily on the use of SCMs for research and investigation. In fact, just about any material since industry, from the aerospace and chemistry to electronics and energy usage, have only been made possible with the help of SCMs. Semiconductor inspection, that is one more application. Reliable performance of semiconductors requires accurate topographical information. The third application is microchips assembly. Microchip production is increasingly relying on SCMs to help gain insight into the effective of new production and fabrication methods. With the smaller and smaller scales and materials, as well as the potential of complex assembly polymers and high resolution three-dimensional capacity of SCMs is invaluable to microscope design and production. Forensic investigation, that is one more application. So analysis of a gunshot residue, jewelry examination, bullet making compression, handwriting and print analysis, examination of banknote authenticity, paint, particle and fiber analysis, filament bulb analysis in traffic incidents. So, now, in biological science also, it is very much useful, measuring the effect of climate of changes of species, uncovering new species, vaccination testing, work within the field of genetics. Medical science, identifying disease and viruses, testing new vaccinations and medicines, testing samples over the lifespan of patients. So these are some of the applications. Now, of course, there are some limitations also. The special training is required to operate SCM as well as to prepare the samples. Maintenance is very, very high, and maintenance involves keeping steady voltage, currents to electromagnetic coils, and circulation of cool water. Finally, SCMs carry a small risk of radiation exposure associated with the electrons that scatter from beneath the sample surface. And also the SCMs are expensive, large, and must be housed in an area free from possible electric, magnetic, or vibration interferences. So these are some of the limitations. Thank you.